So now we start chapter 6, which is circular motion and other applications of Newton's laws. So we'll mostly see circular motion, other applications. Okay, so we'll deal with circular motion here, and then the other applications include what we call fictitious forces and motion through a resistive medium. So the first thing we'll look at is that circular motion. So if we have an object that's, for example, you tie a string to some mass and you make it go around in a circle, so it goes in a circle, then because it's not going in a straight line and it's turning, so there is an acceleration which we already saw, and that was AC, and AC, the centripetal acceleration, was pointed towards the center of this circle, and we found it in the previous chapter to be v squared over r, where r is the radius of the circle. Now we also know that F equals ma, so whenever there's an acceleration, there must be a force. So if you have the centripetal acceleration, we have the centripetal force, and therefore the equation for Fc is m, and the a is replaced with v squared over r, and this becomes what we call the centripetal force. This is a force that pulls this object towards the center. If it did not pull it towards the center, it would have gone straight. So when it's over here, it would have gone straight, but the centripetal force pulls it inwards. So it's constantly pulling the object inwards. And well, that's the direction of the force. So it always pulls in the direction of the force, which is towards the center of the circle. So that's the centripetal force, and we may also add a summation in case there are more forces. Now, in this case of a string with a weight, the centripetal force is the tension for the mass attached to a spring. The centripetal force is tension in this string, and the tension is created by somebody pulling over here. So the centripetal force is the tension. Now in the case of, for example, gravity, for example, you have the earth and you have the moon, and the moon is going around the earth in like a near circular orbit. So it's somewhat similar to this. Here we have a string, here we don't have a string, but there has to be a centripetal force because it's turning. And so here in this case, the centripetal force is the gravitational force. The gravity provides the centripetal force. Now for a car on a curve, so you have a curve and you have a car going straight, and then it turns, so it's going in, like in this part is a part of a circle, so you have a radius. This means there must be a centripetal force pulling it towards the center of that circle, and in this case the centripetal force is the friction force. Friction provides the centripetal force. So when we're going to write the sum of forces equals ma, we will not write a centripetal force and a friction force pulling inwards, but we'll just write one of these, and that is the same as the other, or we'll just write the friction force, which is the centripetal force. Similarly, we don't write the gravitational force pulling inwards and a centripetal force, but we just write the gravitational force, which is the centripetal force. So we'll take an example of this later on. Now we'll look at one special case of circular motion, which is called the conical pendulum. There are many kinds of pendula or pendulums. So one of them, the most simplest, is that if you have a surface and you attach a weight to it and you pull it on one side and let it go so it goes back and forth, that's called the simple pendulum. And then you could also have a rod which has a mass all along it, and there's a pin over here, and that oscillates. So that's a compound pendulum. And the pin doesn't have to be at the top. The pin doesn't have to have this over here. So there's a pin over here around which it's going back and forth. So it's a compound pendulum. And we could also have the pin somewhere in the middle. So you could have a pendulum going, oscillating about this point, back and forth. So this is also a compound pendulum. And this, what we're going to see now, is a different kind of pendulum. It's a conical pendulum. So this conical pendulum will be somewhat like this. So we have a support, and we have a string, and we have a small mass. Well, the mass is not small in size, but it's small in size. It's small in size, but not small in magnitude. So it's a physically small, but not very light mass. And then instead of pulling it on one side, we pull it and give it a push, so that it effectively goes in a circle. So it's circling, and we want to solve for what is the speed. Okay, the speed will be the same all along. We want to find the value of the v, and given the length L and theta. So we know that the faster it goes, the bigger the angle becomes. So if you're spinning this hanging a weight and you're making it go in a circle, if it's going slow, the circle is of small radius. If it's faster, it goes faster. This angle keeps on increasing. Now, before we solve this, I'd like to show a small video of how a conical pendulum would look like. So this is a conical pendulum. So we have a mass that's going around in a circle. The string will have a tension in it. This string will have a tension that's pulling it up. The weight is acting downwards, and the centripetal acceleration is always pointing towards the center of that circle. So because this makes it look like a cone, it's called a conical pendulum. Okay, so now we want to solve this an equation. We want to find an equation between v, theta, and L. So we write, first thing to do, as always, is make a free body diagram. So we have the weight mg acting straight down. We have a tension pulling along the string, that's T, and we set up our x and y coordinates like this. So this is in the y direction, negative y direction, and this is at an angle. So we'll break this up into two components. We'll have an x component, Tx, and a y component, Ty. And then we will write, again, as usual, sum of force in the y direction equals MAY. So we have only one force in the y direction and one in the negative y direction. One in the positive y, one in the negative y. So it's going to be Ty minus mg. Now, this is going to remain in a horizontal circle, so there is no acceleration in the y direction. Therefore, ay is 0, and ty becomes equal to mg.